Hey everyone, here is the video lessons that I've been promising you going over our last practice unit exam on kinetics and equilibrium. So our objective is to revisit the skills needed for success on our unit in kinetics and equilibrium. Question 1. A reaction is most likely to occur when reactant particles collide with Let's take a look at some of these illustrations to assist us. Here is the first one, and this is suggesting that we have right here a nitrogen and another nitrogen, and they are colliding, but yet it is still separate right here. It did not collide with the significant or the correct orientation or energy to change into a new molecule. Whereas in this picture here, right here is a nitrogen and it's facing the other nitrogen. The two nitrogens are facing each other. They collide with sufficient energy and a new molecule is born. This other picture here, let's expand this one, is suggesting something similar. Now remember, at any time you need to, pause and look at the images. Alright, so here reactants are moving too slowly, so that suggests energy. Reactants not facing the right way, and reactant energy and orientation is correct. So, let me make this bigger again. There we go. And this first one can't happen. Not enough energy. This one not facing the right way, the wrong orientation, but this one is just right. And lastly, this image right here. This is our potential energy diagram, and it is showing you that here are our reactants. And the reactants have combined with the right amount of energy and activation energy to get over this hump to become the products. Inspecting the choices now. And we have proper energy only. No, needs orientation. Proper orientation only. Nope. Both proper energy and proper orientation. Question 2. In most aqueous reactions, aqueous, that means something has dissolved. A solute has dissolved into a solvent. We have a solution. So in most aqueous reactions, as temperature increases, the effectiveness of collisions between reactant particles, what might happen? Here's an image to assist us. Here we have on the left low temperature, and yeah, they're moving around. Okay, they might collide in the right way with the right energy. Alright, some reactions are going to occur. But raise the temperature. Those guys are moving. More likely that they will collide with the correct amount of energy and more opportunities to collide correctly. Which one does that? Okay, we have a question. Will it decrease? No. Will it remain the same? No. It will increase. Question 3. At 20 degrees Celsius, a 1.2 gram sample of magnesium ribbon, we use that in class, reacts rapidly with 10 milliliters of 1 molar hydrochloric aqueous. That suggests it's hydrochloric acid. Which change in conditions would have caused the reaction to proceed more slowly? We want to slow it down. Now again, we have magnesium ribbon and we have 1.0 molar hydrochloric acid, and we're at 20 degrees Celsius. Alright, which one of these will make it go more slowly? What are our options? We have increase the initial temperature, increase initial temperature to 25 degrees Celsius. Previous slide showed us, no, increasing temperature would make the reaction go faster. Cross that out. How about decreasing the concentration of HCl to 0.1 molar? Consideration. Looking at number 3, using 1.2 gram of powdered magnesium instead of the ribbon. Well, if we increase or we create a powder, that will increase surface area, allowing the hydrochloric acid to come in contact with more of the magnesium ribbon. That would go faster. And what about using 2.4 grams of magnesium ribbon? Well, that's increasing a concentration. It is not 4, it is 2. Now take a look at this image. Well, which one would have the lowest concentration? It would be this one right here. Let me circle it. Lower concentration, less of a reactant. By the way, the gas that is inside the balloons would be hydrogen gas because it is a single replacement reaction when magnesium reacts with hydrochloric acid. If you recall, table J tells you that because we have hydrogen low on that table while magnesium is higher, saying it's more reactive, so it will take its place. Question 4. Given the balanced equation representing a reaction, we have iron solid combining with 2 moles of hydrochloric acid. It's aqueous, so it's acid, yielding iron 2 chloride, aqueous, and hydrogen gas. The question: this reaction occurs more quickly when powdered iron is used instead of a single piece of iron of the same mass, because the powdered iron, well, let's take a picture of a representation of that. Okay, move this image. Well, let's just shrink it right here. All right, pause this if you need to, but let me describe it right now. Here we have the picture of iron as a solid, and these particles would represent the hydrochloric acid. Now, can these particles of hydrochloric acid come in contact with the central pieces of iron? No. But if we were to powder the iron, notice here in this picture that more of the hydrochloric acid could come in contact with more of the iron. Therefore, the reaction will take place faster. I'm also going to show you this slide here in a moment after we choose our correct answer, just so that you could review from it. And what is the correct choice? Well, why is the powder better? Because acts as a better catalyst. Not even mentioned here. Absorbs less energy. I'm stopping there. Has a greater surface area? Or is more metallic than a single piece of iron? I don't even know what that means. The answer is choice 3. Now, I'm going to expand this one for you. I ignore that little circle there. Get this out of the way and pause it and read through it if you would for other conditions that would affect chemical reaction rates. Number 5. For a given chemical reaction, the addition of a catalyst provides a different reaction pathway that, what will happen? Well, let's take a look at the potential energy diagram. This one here is showing a normal reaction. Here is the potential energy of the reactants. And this here, as this climb, shows you how much energy needs to be added in order for that reaction to take place, so to reach the activated complex. And then once it gets there, the reaction will go downhill, exothermic reaction. It lands right here, giving off this amount of energy. Well, what would make it go faster? Well, if a catalyst were added, our activation energy right here would be lower. Let's see what matches. We have this one here says decrease the reaction rate and has a higher activation energy. Higher activation energy? No. Decrease the reaction rate. Decrease reaction rate? Don't even like that. Increase reaction rate? Starting to like it. And has a higher activation energy? No, that would be harder to take place. Or 4, which obviously is the choice. Increase the reaction rate and has a lower activation energy. Once again, examine this picture and you'll see why. All right, number 6. The activation energy of a chemical reaction can be decreased by the addition of, well, I'm hoping the last slide helped you out, because here's that picture again. What the activation of energy of a chemical reaction can be decreased by the addition of. So here is the activation energy. You can decrease it by adding a catalyst. Which choice? Right there. Question 7. For which compound is the process of dissolving in water exothermic? All right, we have a table that we examined in class called Table I, and it helped us understand some of the reactions if they were endothermic or exothermic. And if you inspect closely near the bottom of that table, it not only tells you that right here, down here, that the delta H values are based on molar quantities represented in the equation, and a minus sign indicates an exothermic reaction. Additional inspection shows you that here are some reactions where water was added, all of these. So we are looking for one with a minus sign to be exothermic, and it has to be one of these choices. So sodium chloride right here. Okay, dissolving in water, a positive sign, not exothermic. NaOH, sodium hydroxide right here, negative sign. All right, let's just hope that there are no more negative sign ones. Okay, NH4Cl, where are you? NH4Cl, another positive sign. NH4NO3 right here, another positive sign. Ding, 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 we have our answer. It is exothermic. Number 8. Given the balance equation representing a reaction at 101.3 kilopascal, that's a unit of pressure, and 298 Kelvin, which statement is true about this reaction? Now we have 1 mole of nitrogen gas combining with 3 moles of hydrogen gas to yield 2 moles of ammonia gas. And, well, we're seeing here that the energy is listed separately. So that suggests that energy has been separated from the substances. So it's on the product side. Don't let this throw you. Even though it says positive, what has occurred is energy has been released. Let me draw this out as a potential energy diagram. It would show this. Here we had the potential energy of the products. We reached the activation energy, and right there. And this suggests that this amount of energy has been released. That's our heat of reaction, which is our delta H. Now it went down. So inspecting these choices, we have it is exothermic for 1, exothermic for 2. We don't like that this says endothermic. Now is delta H positive or negative? Well, didn't it go down? So even though this says positive 91.8, delta H is truly a negative. So the answer is choice 1. Now again to what I just said. Be cautious when identifying exothermic or endothermic reactions when given a chemical reaction such as the one on the last question right here. Keep in mind, in a chemical reaction, chemical equation, the heat will be written as a positive on the right side. This indicates the quantity of energy that has been separated from the substance. That is if this is an exothermic reaction. Now on table I, as identified in the key on the bottom, the energy difference, delta H, for exothermic reactions is written as a negative delta H. Now this suggests that the substance lost that amount of energy. So, once again, here is table I, and right up top here is that equation. Please consider that this positive energy is a loss of energy here, but that is represented as a negative delta H when looking at table I. Okay, here I am down here now. Alright, that's the end of part 1. Please move on to part 2.